look at this exercise which I have created. It's not there in the text, but since we had an issue in the previous videos regarding construction of non-abelian groups from a given group and one of its automorphisms, so we are going to address that issue in the form of this verify exercise, if you want to call it. So on page 69 of the text, we have come across the example of a cyclic group of order 7 generated by A, and it was mentioned that this map is an automorphism of order 3 of that group, and then the author describes a system which he says can be verified to be a non-abelian group of order 21. So we are now going to see those things, because what we have in the text is somewhat casual and vague. Okay, so before we do, so the first thing we are going to do here is we are going to show that phi is a homomorphism. But before we do that even, let us first show that phi is well defined. So capital G is the G that we have there, namely the cyclic group of order 7 generated by A. Then by the rules of exponent, we have so using this equality, you get this. Hence, phi is well defined. Okay. Now next, let's show that it's a homomorphism. And you should understand that I and j are some integers. Okay, not necessarily non-negative integers, are not necessarily restricted in this way. I and j are any integers, and these are integral powers of the element A in G. In that sense, you should understand these symbols, because that's what they are. No, in a cyclic group, when the generator is A, then the group consists of all integral powers of A. Next, we can take something else, I prime and a to the power j prime belong to G. Then this is equal to, using the rules of exponents, we have this. Again, you use the rules of exponent and you can write this thing as this product. This is the phi image of a to the power I, and the other one is the phi image of a to the power j. prime, I prime and j prime. So phi is a homomorphism. Let us next show that phi is 1 to 1, because we need to show that it's an automorphism. Now that we have shown it's a homomorphism, so what's left for us to show are these, that phi is 1 to 1 and onto. So let's show 1 to 1ness first. Belong to G such that their phi images are equal. Then these two things are equal, which implies using the rules of exponent again this. Now from this last equation we get the fact that the order of A should divide this exponent, and the order of A is 7 because A generates a cyclic group of order 7. So as an element of that group, its own order is 7. So 7 divides 2 times r minus s. Since 7 and 2 are relatively prime, since their GCD is 1, so from a previous number theoretic result, we have r minus s. Hence, now since 7 divides r minus s, that means r minus s is a multiple of 7, and 7 is the order of A. So this is equal to identity, or this. So when images are equal, the inputs are also equal. This implies phi is 1 to 1. Okay, now next we want to show that phi is onto. Okay, for that we need, next let, how many more different exponents shall we take? We have taken I prime, j prime, then r and s. Let's take I and j themselves, I mean this, because after all these are variables, these are not constants. I is any integer, b any element, since 2 and 7 are relatively prime, there exist integers alpha and beta such that 2 alpha plus 7 beta is equal to 1. Oh, since 2 and 7 are actually concrete integers, we can write some concrete value of alpha, and but it does not matter. After all, the fact that is important to us is that there are such integers alpha and beta. That's what we need. There is no real need to find some actual alpha and beta. Their existence is enough. Now, a to the power I can be written as a to the power I times 1 2 alpha plus, so in place of 1 we can write 2 alpha plus 7 beta. Now, using the rules of exponents, this can be written as two I alpha times this I beta. This thing will vanish because 7 is the order of A. And we are left with this, which is the phi image of this element. And clearly this, since this, the element inside this function is still an integral power of A, because I and alpha are integers. So this element also belongs to the group G, the cyclic group. So any element in the group has been shown to be an output for some input under the function phi. Thus phi is onto. We have shown that phi is an automorphism of G. The next thing we want to show is that phi is of order 3 for any element in G we have. What happens when we apply phi q to that element? I, then to that we can apply phi once more, and finally then once more. So this is this. So these two and these two get multiplied by one of the rules of exponents. So we get 4i. And just like that, when you apply one more phi, you get one more 2. So you get 8i. And this, if you arrange the things properly, is this, which is equal to a to the power I. So phi q is the same as the identity map on G. But this is not enough to tell us that phi has order 3, because maybe a lower positive integral power of phi is also equal to identity. Let us now show that that is not the case. Since a phi equal to a square is not equal to a, and a phi square equal to a to the power 4 is also not equal to a, we have phi not equal to identity and phi square also not equal to identity. Thus phi is of order 3. Okay, in the automorphism group of G, as an element of that group, phi has order 3. And do you understand why we have these non-equalities? These two are not equal because had they been equal, A would have been equal to the identity, which is not true, because the identity has order 1 whereas A has order 7. For that same reason, that A has order 7, these two cannot be equal, because if they are equal, then A cube should be equal to identity. But that is not possible since the order is 7. So 7 is the smallest positive integer such that the corresponding power of A is equal to the identity. Okay, so we have now shown that phi is an automorphism of order 3. Now we come to that vague part where the author mentions a non-abelian group of order 21. So let us follow his at least the set of formal symbols that he presents, and then okay, so the author starts with a set of formal symbols where the symbols look like this. We are also going to consider that set, and we are also going to consider the criterion for deciding when two such symbols are equal according to the author. But after that our paths will be different. The author after this, after saying all these things, says that these relations are supposed to be satisfied by x and a. Okay, that is the presentation of groups path. We will, however, take a more straightforward path. We will introduce a binary operation on the set of these symbols, show that it's a non-abelian group of order 21, and in which those relations are true. Okay, so that's what we are now going to do. So let us first see the set. Let H denote the set of those symbols, which if we want to write all the things, I think it's better to see all the symbols, I mean the list of all symbols. And then these ellipses indicate clearly the things that we have in between. namely the other powers of A. Yes, we should not actually say powers of A because these symbols are units. We don't have any separate meaning attached to X or A. You can say, of course, A is the, I'm forgetting everything today. A is the generator of the cyclic group, but we are not attaching any separate meaning to X. X, for now at least, for us is a part of these symbols. Okay, so we have A2, A3, all those things are there. Since we don't want to write that many, the entire list we don't want to write, because then we would have to write 21 elements. So we are using ellipses. And then x2, a0, x2, a1, like that, x2, a6. And this sudden introduction of this h is justified by this, because in the text it has been done. Now we are only going to assume the criterion is that the language, assume the definition of equality. Equality of two symbols of the form this from the text. And let us also recall what that definition is. For integers I, j, k and l, we define two such symbols to be equal when I is congruent to k mod 3 and j is congruent to l mod 3. Okay, so this was the criterion for two such symbols to be equal. But since it's given in the text, we are not going to mention it here. Okay. So fine, we have a set of formal symbols and we know in that set when we can call two symbols the same thing, the two symbols equal, and when we can say that two symbols are not equal. So the next immediate thing is just that we have to define a binary operation on this set which will actually give us everything that we want, which will turn H into a non-abelian group of order 21. In fact, just from the before even introducing the binary operation, you can see that by the definition by the definition of this set H and by that criterion for equality, actually there are 21 elements in this set. Of course, you can see here there are 21 symbols, but the definition of equality makes sure that these are all distinct. Okay, any symbol that you see here you take any other symbol that is a different element from that one. Okay, so there are 21 elements in this set, that is already there. From the text, we will not assume the conditions or relations, same thing, equal to we will not make sense of these things. Okay, now itself we will not make sense of these things. For us these are still meaningless and we are not saying these things. These conditions will be properly interpreted only after showing that H is a group under a binary operation that we are now going to define. For two such symbols, xiaj and xkal belonging to H, we define this. Okay, the definition will look extremely strange at first, but it works. I plus k. Is it better if I write it here? I plus k, but this plus is a special type of plus. A to the power, okay, this exponent I seem to never be able to remember. 2 to the power k j plus L. This plus is also a special type of plus. Now we should say what these things are. Where I plus k and are the remainders obtained when this ordinary sum I plus k and this ordinary number 2 to the power k times j plus L are divided by 3 and 7 respectively. Okay, so what is it? We have taken two such symbols from this set. So we know that I is either 0 or 1 or 2 because those are the superfixes of x. Also, j is any integer between 0 and 6. It can be 0, it can be 6, or it can be anything in between. Similarly for k and L. Okay. Now, when someone divides the integer I plus k by 3, one gets a remainder. That remainder is this I plus 1k. Similarly, we have this integer 2 to the power k times j plus L, where because k is either 0 or 1 or 2, so 2 to the power k itself is an integer. In fact, it's a positive integer that you can multiply with j, that is an integer, plus L. So this is again an integer which you can divide by 7. Once you do that, you will get a remainder. This is that remainder. Okay. Now note one thing. Because the number that appears above x is a remainder when we divide something by 3, this itself is either 0 or 1 or 2, because these are the possible remainders when we divide something by 3. Okay, so that means in this symbol the number above x is either 0 or 1 or 2, and those are the things that we see here. Similarly, this is the remainder when we divide something by 7. So this can take these values. So the exponent of a also is the ones that we are allowed to take here in this set. So this is again actually a symbol in H. That much is we are sure of that. Now comes the other part of showing that this operation is well defined. Namely, if you take 4 symbols, such that 2 of them are equal and the other 2 are equal, then we apply this operation, then the results should also be equal, because then only we can say that it's a binary operation, it's a well defined operation, and then we can work with the operation. Okay, so we now turn to that thing. In fact, before saying that, since all these things are somewhat, they look more abstract than what we have been doing so far, so let's write all the things. Since by 3 and 7 respectively, we have okay, so at least the result is again in this set. Next, let us take 4 elements which have been taken like this: I1, J1, I2, J2, K1, L1, belong to H. Such that these two things are equal and these two things are equal. K1, L1, K2, L2. Then from the definition of equality on the set H, we have these congruences. The first equality implies I1 is congruent to I2 mod 3. And here we are not doing anything. This is what the author says. Similarly, J1 is congruent to J2 mod 7. From the second inequality, similarly, K1 is congruent to K2 mod 3 and L1 is congruent to L2 mod 7. Okay, fine. From this, we get what? I1 plus K1 is congruent to I1 plus K1. Let me first write, then I will say what we have done here. I2 plus K2, I2 plus, it's very easy to get confused with this 1 and 2, mod 3. Okay, now our I1 plus K1 is an integer. If you divide that integer by 3, then it is 3 times some integer by the Euclidean algorithm plus the remainder, and that remainder according to these notations is this. So you can see that 3 divides this difference clearly because the difference is a multiple of 3. So this is congruent to this. In fact, any integer is congruent to its remainder when you divide the integer by the modulus, modulo that modulus. Okay, here the modulus is 3, so this is congruent to the remainder. Similarly, this one is congruent to, this number is congruent to the remainder. Now, why is this congruent to this? That is coming by coming from these two congruences. You add them up, you get this thing. Use the elementary properties of congruences. So this is congruent to this, that is coming from adding these two congruences. This is congruent to this because number is congruent to its remainder, and for a similar reason this is congruent to the remainder. Okay. Now next is somewhat more complicated. This is one thing we have got. Now next, if k1 is equal to k2, as integers, as non-negative integers, you see that because k1 and k2 both appear above x, so each one of them is either 0 or 1, 0 or 1 or 2. Okay, so as integers they may or may not be equal. Now if k1 is equal to k2, then we of course have this next congruence: 2 to the power k1 j1 plus L1. Okay, and this is the remainder when we divide the ordinary number, which is 2 to the power k1 j1 plus L1, ordinary plus, by 7. This thing, just like these arguments, is congruent to 2 to the power k1 j1 ordinary plus L1, and the congruence is modulus 7. We will write that at the end of the calculation. Okay, now look at we have already used this modulo 3 congruences. Now let us look at the modulo 7 congruences. J1 is congruent to J2 mod 7, L1 is congruent to L2 mod 7. So if we multiply on both sides of this congruence by 2 to the power k1, then 2 to the power k1 j1 will be congruent to 2 to the power k1 j2, and then with that congruence you add this one. That will tell you that this thing is congruent to k1 j2 plus L2 mod 7, and because k1 is equal to k2, this is, if you want you can write equal to also here, but it does not hurt to write congruence: k2 j2 plus L2, and this thing is congruent to the remainder that we obtain when we divide this by 7, that is k2 j2 2L2 mod 7, and so this is congruent to this mod 7 if k1 is equal to k2. Now what happens if k1 is not equal to k2? If, or let's write like this: next let k1 be different from k2. We assume without laws of generality that K1 is greater than K2. Either K1 is greater than K2 or K1 is less than K2. We have to assume one of them. One is sufficient. Okay. Then, okay, now if K1 is greater than K2, then I have written here that there exists a positive integer s such that then K1 is equal to 3s plus K2. Where is this 3 coming from? That is obviously coming from this congruence. K1, because we have assumed that K1 is greater than K2, so that means K1 minus K2 is a positive integer, and this congruence says that K1 minus K2 is a multiple of 3. So it should be a positive multiple of 3. So that's why there is a positive integer s such that K1 minus K2 is 3s, or K1 is equal to 3s plus K2. Okay. Hence, now what happens to 2 to the power K1? 2 to the power K1 is congruent to this congruence that we are now going to write. This is modulo 7. 3s plus K2 okay. Now this is note that we can write like this and still things will be meaningful inside a congruence, because s is not negative, s is a positive integer, so this power is a positive integer and this of course also is a positive integer. Now this is congruent to 2 to the power K2 mod 7. Why? That is because of this congruence. Note that 2 cube is 8, so that is congruent to 1 mod 7. So that thing vanishes. Now you look at this congruence, and this last one. Hence, 2 to the power K1 J1 plus L1 is congruent to K1 J1 ordinary plus L1. This anyway is true, but now this is again just like this case is congruent to 2 to the power K2 J2 plus L2. In this case K1 and K2 are not equal, so 2 to the power K1 and 2 to the power K2 are not equal, but they are congruent to each other mod 7. So we multiply this last congruence with this one, and then with that product we add this congruence, so we will get this thing. Finally, plus L2 mod 7. Let us now use this congruence, that is this thing congruent to this thing mod 3 and this thing congruent to this thing mod 7, which we have shown is true in both the cases. So in general also it's true. To conclude this, we thus have I1 a to the power j1 k1 a to the power L1, let's not say to the power. By the definition of our operation, because this is congruent to this and this is congruent to this, so this symbol is equal to, according to the definition of equality on the set H, equal to this. And this symbol is nothing but this product. Okay, let me just see it from a distance. It's very easy to get confused in all these symbols. 1, 2, ijkl, ijkl, yes. So now we see that same symbols give us the same value of the operation. Hence, the operation defined above is well defined. Okay. Next is associativity. For associative law also we have to put some effort. Next, let alpha be the symbol xiaj, beta be the symbol xkal, and gamma be the symbol, what have I taken, xu, okay, xman in H. Then, okay, so let us now start our calculation. We first start with this alpha, beta, gamma. Let us carefully write the symbols first. So the first product is this I plus 1 k a 2 to the power k j plus L. Have I written it correctly? Yes. then this. Once more, if we do this, we get I plus k plus m, and then a 2 to the power m times 2 to the power kj plus l plus 2n. So far we have just applied the definition of our binary operation. We haven't do anything else. I mean, we haven't done anything else. I'm forgetting grammar also. Next are some steps which we will have to justify later. First, let us write the calculation down fully, and then we will see what we have done. The first thing I will do is I will simply write the first superfix like this, as if the operation plus 1 is associative. We have to justify all these things, okay? And then in place of this we are writing 2 to the power m plus 1k. All these things may look extremely weird, almost out of the blue, but we will see that it works. Plus 2, then 2 to the power m l plus 2n. Of course, to show that this step is justified, you have to show that this integer is congruent to this integer mod 3, and this integer is congruent to this integer mod 7. That's what we will show afterwards. But let us now go back to alpha, beta and gamma. What happens if I write in place of all these things something like this? K plus m a 2 to the power m l plus 2n. From here, if I start and I apply my definition of our binary operation, do we get this? Let us see. I plus 1 k plus 1n. Okay, so there is no problem with the first one. Then 2 to the power this times j plus 2 this thing. Okay, so it matches with our definition of the binary operation. Now you can see that what we have here, the second factor is actually itself the product of these two things, AL XMA N. K plus 1 M 2 to the power m times L plus 2n. So this is alpha times beta gamma. Okay, but what is the justification of these steps? Are they really true? Let us now justify the above calculation. Note that the first one is easy. We have to show that these two things are congruent to each other, mod 3. So I plus 1 k plus 1 m. This is congruent to the integer which when you divide by 3 gives you this remainder. That means you can we have already seen that when we have something like this, we can remove the suffix 1 from the class. That you can do here also. If you find it difficult to understand how this thing is congruent to this, you first think of k plus 1m, that is congruent to k plus m mod 3. Add I on both sides, that's it. Okay. And now since this is ordinary addition of integers is associative. So this is I plus k plus m, which is congruent to I plus 1k plus m, which itself is congruent to I plus 1k plus m mod 3. So there is no problem with this part. Now we come to this part. For that, so we have started our thing with this integer. Since this is congruent to, I think in the first few steps we are just removing those suffixes to. Yes, since this is congruent to which is congruent to plus n, and that is congruent to 2 to the power m plus k times j plus 2 to the power ml plus n mod 7, and if we start with this one, m plus 1k times j plus 2 plus n, and this is congruent to, note that we cannot really remove this one because it's in the exponent and we don't really know about what is going to happen to this if we remove one. So we just keep it like this, but here of course we continue removing the things. Mod 7. So you can see that what is our aim? Our aim is to show that this integer is congruent to this integer mod 7, but this is congruent to this final expression. In fact, for our benefit and to distinguish things properly, let me use brackets. This integer mod 7 and this one is congruent to this mod 7, so it's enough to show that these two things, these two final integers are congruent to each other modulo 7. Now they look almost like each other except for this part. In one of them we have ordinary m plus k, and in the other we have the remainder when m plus k is divided by 3, because by 3, because here the suffix is 1 not 2. Suffix 2 means division by 7, suffix 1 of plus means division by 3. Now if we can show, because the other things are the same, are exactly equal actually, 2 to the power ml, 2 to the power ml, n, j, j. If we can show that this power of 2 is congruent to this power of 2 mod 7, then our job is done. And this it's enough for what? To show now we have reduced things to this level. Now here it's not very difficult, since m plus k itself is congruent to m plus 1k mod 3, there exists a non-negative integer t such that m plus k is equal to 3t plus m1 m plus 1 k. But why non-negative? Without t being non-negative, we will have problem. Okay, let me think about this non-negativity. Why should t be non-negative? T is non-negative only when m plus k is greater than or equal to this remainder. I am missing something obvious, of course. M plus k, okay, m and k, each one of them can either be 0 or 1 or 2. So these are the possibilities for m, these are the possibilities, also the possibilities for k. Now when when both of them are 0, then of course m plus k is 0 and the remainder is also 0. Fine. If m is 0 and k is, in fact there is no need to see all the cases. M plus k can have how many different types of values? M plus k can be 0 or 1 or 2 or 3 or 4. Okay. Three or 4. So when we divide this by 3, the remainder is, these are the remainders, okay. On division of these numbers by 3, remainder is 0. When we divide this by 3, the remainder is 1. When we divide this by 3, the remainder is 2 itself. Here we get 0 and here we get 1. So we see that the remainder in each case is less than or equal to m plus k. So that is why t is non-negative. Since there are only a few cases, so we can just see like this. Hence, 2 to the power m plus k is congruent to, now our congruence is modulo 7. 3t plus, now you can almost see that it's a situation like what we had before. This is congruent to 1k. Now 2 cube is congruent to 1 mod 7, so this is equal to 2 to the power m plus 1k mod 7. So because of these things, we have what we wanted to show, and that's why that step is justified. That step is justified means that was the only step which we needed to see is true. So our Above, I don't know how to say this. Above calculation means the one where we showed that the operation is associative. Above calculation, in fact, let's mention that where we this is justified. So our operation is associative. So we have now shown that the operation is associative. Next, identity. The element x0 a0 can easily be shown to be the identity, or we should not write the identity, because uniqueness of identity comes only after proving that the system is a group, is an identity. Also, for xij belonging to H, we haven't directly said anything about the inverse, but rather we have found the inverses of all the elements. Next, for xij and xkal belonging to H, the equations xkal equal to, so here we want these two elements to be inverses of each other. So we have this, and also at the same time these equations are equivalent to these congruences. What you do, you just apply the definition of our binary operation. You will have an expression here. Similarly, you will have an expression here. From this equality and this equality, you then apply the definition of equality of two such symbols in H, and once you do those things, you will have these congruences equivalent to I plus k congruent to 0 mod 3 and 2 to the power k times j plus l congruent to 0, which is also congruent to 2 to the power I times L plus J. mod 7. Okay. Now the question is, can we really, if we for example choose xij in H arbitrarily, for such an element, does there exist an element which behaves like its inverse? Because then only we will have inverses for all the elements. So everything now boils down to the system of these congruences. The solutions IJKL to the above system of congruences are these: 0j 0 7 minus j, where j lies between 0 and 6 when I and k are themselves 0. When I and k are 0, then these are the solutions. Then for any j you choose between 0 and 6, L will be 7 minus j. And when they are not 0, and the remaining solutions are, which unfortunately I haven't been able to find any pattern to write the remaining solutions in a systematic manner like this. I just had to write all the solutions like this, like 4 vectors, and they are precisely 1 0 2 0. To see that excuse me, they are solutions, you have to actually verify all the cases. 1 1 2 3, then there are quite a few. In these remaining solutions, I and k are not simultaneously 0. One of them may be 0. For example, okay, we haven't written that here yet. Because I and k satisfy this congruence now. So if one of them is 0, then so is the other. So either both of them are 0 or both of them are non-zero. Keep also in mind that I and k, each one of them is either 0 or 1 or 2. So that thing is also there. So that's why here in the remaining solutions, both I and k are non-zero. 1 1 2 3, then 1 2 2 6, then 1 3 2 2, 1 4 2 5, 1 5 2 1, 1 6 2 4, 2 0 1 0, then 2115, then 2213, 2311, 2416, 2514, and 2612. Okay. Hence, every element of H has an inverse in H. For example, let us illustrate these things with one instance. For example, the solution any one of them we can take. We have taken here 1 3 2 2. Corresponds to these equations. Ij KL then KLIJ. Which you can verify is true. In fact, let us just see. One thing is obvious, namely the number that comes above x. 1 plus 2 is 3. 2 plus 1 is also 3. When you divide 3 by 3, the remainder is 0. So according to our definition, we will have 0 here. Okay. Now what happens to the number that comes above a? From this calculation, we will have 2 square times 3 plus 2. 4 times 3 is 12. 12 plus 2 is 14. When we divide 14 by 7, the remainder is 0. That means this thing is 0. Or this is equal to 0. What do we get from this calculation? 2 to the power 1 times 2 plus 3. 2 times 2 is 4. 4 plus 3 is 7. Again we get 0 remainder. So you see that the inverse of x1 a3 is x2 a2. So like that, all the other inverses are available here for every symbol. So that's why all the elements of H have inverses. We have now completed showing that H is in fact a group, and since it has 21 different elements, so its order is 21. Okay. Thus, H is a group under the operation we have defined. Also, the definition of equality of two symbols in H shows that the order of H is 21. Okay, so what else? There are now two more things for us to do. One is that we now have to show that H is a non-abelian group, and the second thing we have to show that those relations, we have to make sense of those relations. First of all, what do they mean in this group? So let us first make sense of those relations. We now define X to mean this symbol x1a0 and A to mean the symbol x0a1 and E of course to mean the symbol x0a0, because usually E denotes the identity in a group. With these, one can now verify that x cube is equal to E, because now we know what x is. X is this symbol. We can determine x cube in our group. You will see that it becomes equal to E, and x inverse, is it x inverse A? Yes, x becomes a to the power 2i for any integer I. Okay, these things can be verified, means I leave these things to you, because now you know everything. You know the binary operation, you know the meanings of x, a individually. So you just have to show that these calculations hold true. Finally, H is non-abelian because Ax is not equal to xa. Ax means this times this, and xa is the other thing. These two operations don't give you the same result, and that's why the group is non-abelian. So what have we achieved? We have shown that we have just simply verified what has been said in the text, that the function phi defined like this is actually an automorphism of our cyclic group of order 7, and we have shown that the set of formal symbols can be turned into a group of order 21 which is non-abelian, and in which the mentioned relations are true with these meanings of these symbols x and a. Now the big question, how did I find these things? And the answer is I was not able to find, I was not able to manage all the things for months. I kept racking my brain for that binary operation. Okay, so it took quite a while to actually find the binary operation that will work, that will make things work. I can't tell you exactly what made me choose this I plus 1k and 2 to the power k, all those things, but you can pretty much guess that I took help of these relations. Now, one does not have to go through all this trouble if there is presentation of groups. Unfortunately, that is not there. So this somewhat unappealing path had to be taken, because all these things, you see, we have done everything that the author says in our own way, but this is a very straightforward, dull and extremely ugly way of doing things. It's not efficient at all. There is no clear way of knowing what the binary operation will be that will give us all the things we need, but that is the best we can do with what we have so far. Now, one question still remains: what is the role of this automorphism in all these things? We don't see how phi being an automorphism played any role in creating this group. That will become clear when we see the next thing, where we discuss the general case, namely where we have a group G which need not be cyclic, it need not be finite also, but there is an automorphism T of G which is not an inner automorphism of G. Then the author says that we can construct a group like this, okay, using G and T, which will be non-abelian even when G is abelian, and in such a way that G can be realized as a subgroup of this, in the sense that G will be isomorphic to a subgroup of this large group, such that G is normal in this, and when one forms this quotient, then the quotient becomes isomorphic to the cyclic group generated by T in the automorphism group of G. One more thing is that T, besides being a non-inner automorphism, has finite order, some order R. Okay, so that thing, when we get to this and when we achieve all these things, then we will see that this example is actually a special case of this. There only we will see the fact that T is an automorphism really plays a role in creating this group. It's that in this specific example, you don't see what is happening. Where this automorphism is playing a role, that is not clear in this particular example, but in the general case is like going high above all the things and then having a bird's eye view on the entire situation. So there you see all the parts and you see why something is working. Okay, so that I don't think we will do today. So let all these things sink in first. Let us give ourselves some time, and also you please verify for me that at least these things are actually solutions. Maybe not all of them, some of them, okay, and you go through the entire thing carefully once, seeing that whatever we are saying here is true, is logical and there is no mistake, that is because this is something that has been concocted by me. So naturally there may be some mistakes. If there is a mistake, God forbid, or Lucifer forbids, we will have to modify everything. So hopefully that won't happen. So we will see the general thing in the next video. So until then, it's me, Lucifer, from a mathematical room. Have a nice night.